Okay, welcome to lecture 6 in unit 1. And so in the last couple of lectures we've learned methods to solve two different types of differential equations. We've learned the method of separation of variables for separable equations, and then in lecture 5 we learned how to solve linear first order ODEs using the integration factor method. So we already have a way of solving multiple different types of ODEs, but if it turns out that our ODE is neither separable or first order linear, then at the moment we don't have any way to solve that type of equation. So in this lecture today we're going to learn about a new type of equation called an exact equation, a first order exact equation, and we're going to show you how to check whether an equation is an exact equation, and also we're going to learn a method of solution to solve an exact equation. Okay, so this is just adding to our ability to solve different types of differential equations, and again it's really important that you are able to classify these differential equations according to type. Okay, so first order exact equations. So let's consider if we had some function f of x, y, so some function of two variables, and we can take the differential of this function. So if we call this function z, we can take the differential dz according to the second year calculus. Second year calculus tells us how to calculate the differential of a function of two variables. So the differential of z equals the partial derivative of the function f with respect to x multiplied by the differential dx plus the partial derivative of the function with respect to dy with respect to y multiplied by the differential dy. Okay, so this should be, well, if it's not known to you, then this is how we calculate the differential of a function of two variables. Okay, well, in the very special case that this function f of x, y is actually equal to a constant, so for example, a constant where c is a real number. So for example, a circle, you have this function f of x, y equals x squared plus y squared equals c. So this would be the square root of the radius of the circle. So in this very specific case where our function equals a constant, then the differential is going to be 0, right? So if we take the derivative or the differential of the left hand side here, well, we get something, and if we take the differential of the right hand side here, because this is a constant, all the derivatives are going to be 0. So we're going to end up with df by dx times this differential dx plus df by dy, the partial derivative df by dy times this differential dy equals 0. Okay, equals 0. We can rearrange this equation. We can rearrange this equation like so. Dy by dx equals negative partial derivative of f with respect to x divided by the partial derivative of f with respect to y. And this itself is just simply a first order ODE. The partial derivative of f with respect to x is just some function of x and y. The partial derivative of of f with respect to y is just some function of function of x and y. So this can be a linear or nonlinear ODE, but the point is it's a first order ODE. So given a one parameter family of functions, f of x, y equals c, so for example, a circle, x squared plus y squared equals some constant, from this function, in the very specific case when this function is equal to a constant, we can always obtain this first order ODE. Okay. Well, it's kind of messy always writing these partial derivatives, so I'm going to give each of these a name. So instead of writing df by dx and df by dy, the partial derivative of f with respect to x and the partial derivative of f with respect to y, I'm going to give them actual names now. Oops, I went too far. So df by dx now, the partial derivative of f with respect to x, I'm just going to start calling that m. And the partial derivative of f with respect to y, I'm just going to call that n. So I can write my differential equation like so. dy by dx equals negative m over n. And so I can rearrange that equation. I can multiply both sides by n. I can multiply both sides by x and then take whatever's left on the right hand side over to the left hand side, and I can express this first order differential equation in this form. This function m times dx plus n times dy equals 0. Okay, and we can always find a function. So if we're given a differential equation in this form, then we can find a function f of xy equal to a constant, which is a differential defined by this equation, equation 1. Okay, so this is true for linear or nonlinear functions. Okay, so the previous method of solving first order linear ODEs, the integrating factor method, that only worked for linear first order ODEs, whereas this the method we're about to learn works for any kind of exact equation, linear or nonlinear. Okay, so what do I mean by exact equation? Well, let's define that. So a differential form, or this is what we call a differential form, but let's not worry about the terminology for a moment. So this thing, which we're calling a differential form, is an exact differential form in a region of the xy plane if there is a function f of xy such that the derivative or the partial derivative of this function with respect to x is equal to this thing m, this function m. The partial derivative of f with respect to y is equal to this function n, this thing n over here, for all x and y in this region. Or in other words, we can write the differential of this function f is equal to m times dx plus n times dy. And if this is equal to 0, if m dx plus n dy equals 0 is an exact differential form, then we say the equation m dx plus n dy equals 0, and we call this equation here an exact equation. Okay, so hopefully it'll be a little bit clearer when we see an example here. So here we've got some function multiplied by dx plus some function multiplied by dy. So if we look at the previous slide here, the thing multiplying dx we were calling m, the thing multiplying dy we were calling n. So we have some function m here and some function n here. So this equation is exact because I can find a function. Okay, I haven't told you how I found this function, but I can find a function f, which is x squared y squared plus x, such that if I take my partial derivatives, df by dx is equal to, well, 2x times y squared plus 1, 2x y squared plus 1, is exactly equal to this term here, m, multiplying the dx. Or if I take the other derivative, df by dy, so df by dy is just 2 times x squared y, 2 times x squared y. This is exactly equal to the thing that's multiplying the dy up in the ODE up here. So because I can find a function f that has this property, that its two partial derivatives equal the two terms multiplying the differentials in the equation, then I can say that this is an exact equation. This differential equation up top here is an exact equation. Okay, so I can tell you I can tell you that this is an exact equation because I could find a function f here, but I haven't yet told you how I can find this function f. So that's what we're going to move on to now. Okay, so how do we find this function f of xy to these exact equations? So first we better check actually that we have an exact equation. So firstly, is the equation we're given exact? So let m and n be continuous functions with continuous first order partial derivatives in some region in the xy plane. So x is between two numbers a and b, y is between two numbers c and d. Then a necessary and sufficient condition that this equation m times dx plus n times dy equals 0 is an exact equation. So if this equation is an exact equation, then this relationship is true. The derivative of m, the function m, with respect to y, the partial derivative of m with respect to y, is exactly equal to the partial derivative of n with respect to x. So just take a moment to look at the order of this thing. So the equation, which is potentially exact, is m times dx, but the test to see if it is exact is we take the partial derivative of m with respect to y. So we're multiplying here by the differential dx, but the partial derivative is with respect to y. Similarly, the function n is multiplied by the differential dy, but the partial derivative here is taken with respect to x. So why is this true? So what I'm claiming is, if I'm given an equation that in this form here, this first order ODE, potentially nonlinear ODE, I can check it if it's an exact equation by checking the partial derivatives, checking if the partial derivatives are equal here. So let's prove that that's true. So let's assume for a sec that m times dx plus n times dy is exact. Then we know that this differential df, which the definition of df is the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Of course, this is equal to m times dx plus n times dy. Okay, well, I can take this term here, m, because m is just df by dx, and then I can take its derivative with respect to y, right? So dm by dy is simply the second derivative of f, right, with respect to, well, one derivative with respect to x and one derivative with respect to y. Similarly, I can take my function n, which is already a partial derivative of f with respect to y. I can take the derivative of n, the partial derivative of n with respect to x, and I know that I can write that as partial derivative of f, sorry, two partial derivatives of f, the mixed partial derivative, one derivative with respect to x and one partial derivative with respect to y. And from first year calculus, we know that mixed partial derivatives are equal. So equality of mixed partial derivatives, it does not matter which order we take the second partial derivative. So if we take the partial derivative of f with respect to x and then with respect to y, that's exactly the same as if we take the partial derivative of y and then take the partial derivative of x. Really, the point is, if we are given an ODE, a first order ODE, linear or nonlinear, we need to check if it's an exact equation by checking the partial derivatives of these functions. Okay, this is our test for exactness. Okay, so if we in fact do have an exact ODE, an exact partial ordinary differential equation, by the fact that these partial derivatives are equivalent, then the equation is exact, then we can always find a function f of xy such that the differential of this function f is equal to m times dx plus n times dy. Okay, so the question of how do we actually find that function f? Well, firstly, we know that this function m is equal to the partial derivative of this unknown function f with respect to x. Okay, so we can integrate this function, right? We could we can integrate both sides of this equation with respect to x. So if we integrate, if we integrated the left-hand side with respect to x, then we would get simply f back. If we integrate the right-hand side with respect to x, we get the integral of this function m times dx. But we now also get an extra little function here. We get, instead of, if we do a normal integral of a function of one variable, we'd normally get an integration constant, right? But here we actually get an integration function, or an unknown function of y. Okay, and the reason that is because m here was a function of x and y, but our integral was only a function was only evaluated with respect to x. So this unknown function of y is needed because the integral was only performed with respect to x, but m is a function of both x and y. So we get this sort of hangover function here, g of y. Okay, so now we have an expression for f. We can evaluate this integral of m dx, which for a specific ODE is known, so we can integrate this this function m. But now we have this function g, g of y, which is a complete unknown. So, well, we have to try and figure out what g of y is. So what we're going to do is we're going to take this function f that we've just defined, and we're going to differentiate it with respect to the other variable. So we're going to differentiate it with respect to the variable y. And if I do that, I get df by dy equals the partial derivative with respect to y of this thing here, this right-hand side, integral of m dx plus this unknown function g. And so now it's a partial derivative, so we're taking the partial, we can rewrite this as the partial derivative of this integral of m dx plus, well, g was only a function of y, it wasn't a function of x anymore. So, it wasn't a function of x, so we can just write this as g prime y, knowing that because y is the variable, g prime is just saying this is representing the derivative of g with respect to the variable y. Okay, so the other thing is, right, we already know that from the definition that df by dy, the partial derivative of this function f with respect to y, is nothing other than this thing n. So we now know that this right-hand side here, this partial derivative with respect to y of this integral of m dx plus g prime of y, this is equal to n. Okay, so n is equal to this partial derivative. But again, in a specific case where we have an ODE, we already are going to know what n is equal to. So actually what we can do is rearrange this equation for g prime. So if I make g prime the subject of this equation, then I get g prime is equal to n, take away this partial derivative with respect to y of the integral of m dx. And again, I can then evaluate what g is by integrating both sides with respect to y. So again, since the left-hand side of the equation is independent of x, so there's only y's on this side of the equation, and because it is an equation, there's an equality here. If the left-hand side is only a function of y, then surely the right-hand side must only be a function of y as well. So we can integrate both sides with respect to y without issue. So the g prime is equal to n minus the partial derivative with respect to y of the integral of m dx. If I integrate both sides with respect to y, well, the left-hand side becomes integral of g prime with respect to y is just g. The integral of the right-hand side becomes the integral of n minus this partial derivative with respect to y of the integral of m dx, that integral with respect to dy. That will give us an expression for g, this g function, and we can then substitute this function g into the very first equation we wrote down for f. F is equal to the integral of m dx plus what was previously unknown, this function g, well, we can find g in this way. The final step is saying, okay, well, now that we've evaluated this function f, the actual solution to the exact ODE is take that function that you found at f and set it equal to a constant. Okay, so well, there are a lot of parts to this solving a first order exact equation, and I imagine that at this point in the video you're a little bit confused because, well, it's the first time you've heard it. So I think let's just summarize what we've just said, and then let's do a couple of examples which I think will clear things up. So given a first order ODE of this form, we have some function times dx plus some function times dy equals 0. Firstly, check if these partial derivatives are equal. So take this function m, which is multiplying dx, and calculate its partial derivative with respect to y. Take this function n, which is multiplying dy, and calculate its partial derivative with respect to dx. If these two partial derivatives are equivalent, then we have an exact equation here. If they're not equivalent, then we may have to try another method. Okay, so let's assume that we do this test, we calculate these partial derivatives. These partial derivatives are equal. We therefore have an exact equation. We can move on to step 2. We know that df by dx equals m. By definition, the partial derivative of this unknown function f with respect to x equals m. So we're going to integrate to find f. So f equals the integral of this function m dx plus some unknown function g, where g is just a function of y only. So now we need to find an expression for this function g. We're going to differentiate f with respect to y. Okay, and so df, partial derivative of f with respect to y, is equal to the partial derivative with respect to y of this integral m dx plus this g prime, so dg by dy. And again, we know this is equal to n of x. Okay, this function n being the function that's multiplying dy. We're going to rearrange that equation to make g prime the subject of the formula, just using a little bit of algebra, and then we're going to integrate both sides of that equation. And then so that integrate both sides of the equation, that gives us an expression for g. The left-hand side will be equal to g if we integrate that. And therefore, when we find this value, this function g, we're going to use that value, that function of g, in this equation that we defined up here. Okay, and then that will give us an expression for this unknown function f, which we can set equal to a constant, which is the solution to our exact first order ordinary differential equation. Okay, so let's look at some examples, because I think that's the only thing that's going to clarify what we've just been talking about. So we're given this differential equation, 2xy plus 3 times dx plus x squared minus 1 times dy equals 0. And we want to know, firstly, is this an exact equation? So, well, let's identify our functions m and n. So m is just the stuff that's multiplying the differential in x, so dx. So m is 2xy plus 3. N is the stuff that's multiplying the differential dy. So n is x squared minus 1, as I've written here. The test for exactness says that I should take the partial derivative of m with respect to y and of n with respect to x and check that they're equivalent. So if I take the partial derivative of m with respect to y, I just simply get 2x. If I take the partial derivative of n with respect to x, then I also get 2x. So in this case, the partial derivative of my, the partial derivative of nx, they're both equal to 2x. These partial derivatives are equal, therefore the equation is exact. Good. Step 2, we know that we can define this function f as this unknown function that we're trying to find f as the integral of m dx plus some other unknown function g, which is a function of y only. Okay, well, m we know already is 2xy plus 3, so I can write this as f is equal to the integral of 2xy plus 3 dx plus some unknown function g of y. And of course this integral is quite easy. This term here, 2xy, if I integrate that with respect to x, is simply going to be x squared times y, plus the integral of 3 is just going to be 3x. So our function f is equal to x squared times y plus 3x plus some unknown function g of y. Okay, so now we need to figure out what this unknown function g of y is. So I'm going to differentiate this expression for f with respect to y. So df by dy is equal to, well, if I differentiate this, well, this first term here is, if I differentiate that with respect to y, it's just going to be x squared plus, well, if I differentiate this with respect to y, it's going to be 0. So I'm going to get x squared plus g prime of y. Okay. And we also know that the partial derivative of f with respect to y is equal to n. So this partial derivative of f with respect to y is equal to n, and we have an expression for n from the original ODE, the original exact ODE, the exact equation. We already know that n is x squared minus 1. So if I add that in here, well, okay, I can rearrange it first. G prime is equal to n minus x squared, and I can say, well, n is equal to x squared minus 1. So x squared minus 1 minus x squared. In fact, the x squareds here are going to cancel out, and we're just going to get left with minus 1. So it turns out that g prime, the function g prime of y, is just a constant equal to minus 1. So I can easily integrate this this function g. The unknown function g is just the integral of g prime with respect to y, which is just the integral of negative 1 with respect to dy, which of course is just negative y. So this unknown function g is now identified as just being simply negative y. So now I can use this previously unknown function g in my equation for f up the top here. So therefore, f of xy equals x squared times y plus 3x plus the unknown function g we now know is negative y. Okay, so the solution to the differential equation, the original differential equation, is found by setting this function equal to a constant. So therefore, x squared times y plus 3x minus y is equal to some constant. And again, if we had an initial value problem, we could find the value of this constant. But here we just have an ODE, so, well, it's just a one parameter family of solutions. We can, of course, rearrange this equation to make y the subject to the formula. And if I do that, I get c minus 3x over y is equal to c minus 3x over x squared minus 1. So we find a one parameter family of solutions to the exact ODE. So I feel like there are, well, I know that there are a lot of steps in solving these first order exact equations. So in terms of difficulty, it is a step up from separable equations, it is a step up from first order linear equations. Well, let's do another example just to try and solidify this idea. So we're given the differential equation cosine x times cosine y plus 2x, all times this differential dx, minus sine of x sine y plus 2y times dy equals 0. It's clearly a non-linear first order ODE. It's clearly not separable. Well, in fact, you should try that. Feel free to try to separate these variables, but you won't be able to. It's clearly not linear, so we can't use the integrating factor method. So we should check to see if this equation is exact, and if it is, we can solve it. Okay, so let's identify our functions here. The function multiplying dx is equal to cosine x cosine y plus 2x, and we call that m. The function multiplying dy is equal to negative sine of x sine of y plus 2y. So we call that function n. We calculate the partial derivatives of m, so dm, a partial derivative of m with respect to y, the partial derivative of n with respect to x, and we find that my, so that partial derivative is equal to negative cosine x sine y, and similarly nx is equal to the partial derivative of n with respect to x is equal to minus the cosine of x times sine of y. So clearly these two partial derivatives are equal, therefore this nonlinear ODE, first order ODE, is exact. The equation is exact. Okay, and if the equation is exact, we know that we can find some function f, which is equal to the integral of m dx plus some unknown function g of y. M, of course, is just this, this cosine x cosine y plus 2x. So we're integrating this function with respect to x. Again, it's not too hard. The integral of cosine x is just sine of x. Well, this term doesn't depend on x, so we keep it as a constant. The integral of 2x is just x squared. And we're still carrying around this unknown function g of y. So we have an expression for f now, but we just need to figure out what this unknown function g of y is. So to do that, we're going to calculate the partial derivative of this function f with respect to y. Okay, so if I do that, if I differentiate this function with respect to y, cosine y, the derivative of that becomes negative sine of y. X squared becomes 0 because it has no dependence on y. And this unknown function g of y becomes g prime of y. Again, we know that this partial derivative df by dy is equal to this function n by definition. So we can set this thing that we've calculated from, we've taken the derivative of f with respect to y, the partial derivative. We can set this thing equal to n. We can rearrange to make g prime the subject of the formula. So g prime equals this function n plus sine of x times sine of y. And now I can substitute in the expression for n, which is already known as negative sine of x sine of y plus 2y. Again, this is quite nice because you'll notice that the sine terms cancel out. We have a negative sine x sine y, we have a positive sine x sine y, and we're simply left with negative 2y here. So g prime is equal to negative 2y. Okay, so to find g, I just simply have to integrate this g prime with respect to y, which is just the integral of negative 2y, which of course is just negative y squared. So our unknown function g is now known. G is equal to negative y squared. So therefore our function f is equal to sine x times cosine x plus x squared minus y squared. Okay, and therefore the solution to the nonlinear first order exact ODE is f is equal to a constant. So sine of x times cosine y plus x squared minus y squared equals some constant. So we have a one parameter family of solutions here. There is no way to rearrange to make y the subject of the formula. It's too nonlinear. Y is tied up here in the squared term. It's also tied up here in the cosine term. So there is no way to write y equals some function of x. Therefore, our solution is an implicit one. So I've just given you two examples of how to solve an exact equation. Okay, firstly, how to test if an equation is exact. Secondly, how to go about solving that exact equation if it is exact. Remembering that this method works for any kind of exact first order ODE, linear or nonlinear. So this is the advantage over the integrating factor method. is that it actually works for nonlinear first order ODEs if it happens to be exact. Although I would say that it is quite a lot of work, right? And it is easy to make mistakes using this method. So my suggestion to you would be to do as many examples as you can. To look through the textbook and the study guide, and again, feel free to get in touch if you have any questions. Feel free to post questions on the stream site, on the forum. And just to finish today, I'd like to point out that, well, when we solved this equation, we did this by calculating df by dx is equal to m. We could have also done this backwards. We could have started, instead of integrating df by dx equals m, we could have started by df by dy equals n. We could do it backwards. There's no problem here. In that case, we would have got f is equal to the integral of n with respect to dy plus some unknown function of x. You may like to try to prove that you can get the same solution either way. But the point is, it will work either way. So thank you for your time, and I'll see you in lecture number 7.